So, we will begin our understanding of Sylow theorems. So it is the theorem which is very important, especially the application of this theorem rather than the actual proof. But we will get along with the proof as well. So the theorem goes as follows. These are called Sylow theorems. So let G be a finite group of order p power a times m, where p does not divide m. That means a is the largest power of p such that p divides order of g. Then number one is that the set of Sylow p subgroups. So that means you collect all the Sylow p subgroups of G given by. So this is the set. So Sylow groups are of order p power a. Remember, a is the largest power of p, such that p divides order of G. So if you start by collecting all the Sylow groups, so the natural question here is, do we even have one Sylow groups to start with? And the answer is yes. So that's what Sylow's theorem says, that this set is non-empty. That is, in other words, G has a subgroup of order p raised a. Moreover, so now we have Sylow subgroup, at least one of them. Now if there are two or more than two, then what happens is that all of them are conjugates. So all elements of so these are conjugates in G. Lastly, the question is how many of them are present, right? So the number of Sylow p subgroups will be denoted by NP, n subscript p, and it is the cardinality of, in fact it is the size of the set. Moreover, it satisfies, means the number is given as follows, that NP is 1 modulo p, and NP divides the order of G. So now NP does not divide. So the question is P a factor of NP? So P is not a factor of NP because P divides NP minus 1. So NP cannot be so P does not divide NP. That simply means that GCD of NP and P is 1. So GCD of NP and P is 1. right? So P does not divide NP. The question is NP divides, does that imply that GCD of NP and P power A is 1? P is a prime number, right? So for if this is not 1, then there exists x and y, so x times np plus y times p power a is some d, right? So that means, so d has a prime factorization, and we can approach in this direction, but it looks like that we are not going to get anywhere near to what we wanted, right? So what we have to show is that what I wanted to show is that NP divides M. So we have to just show that this NP, P is not a factor of NP. That is true. Okay, so P does not divide NP. So NP does not divide P power N at all. For if it does, then NP has to be 1, and if it is 1, then certainly NP divides M. So if NP is more than 1, if NP is more than 1, it can be, and it does not have a factor, so NP, so P does not divide NP. So for if it did, then P would divide NP, and that is not possible because NP is 1 mod P. So that means NP divides M, because NP divides order of G, that is P power A. M is NP times some K, right? Since NP does not divide P power A, and so their GCD is 1, so NP times x plus y times P power A is 1. So I will just multiply M on all the side, so that's M. Okay, so P power A, M is order of G, so y times order of G plus NP mx is M, but NP divides order of G, so again there is NP times y times some U, which is M, and mx NP. So you can take out NP, and then you have mx plus yu is M. So that means NP divides M. So this is a deduction from the third theorem. The first one is called Sylow's first theorem, and the second one is called Sylow's second theorem. The third is naturally Sylow's third theorem. So here are some lemmas that we wanted to show. So before proving the result, we wanted to deduce some facts. So if number of Sylow P groups is 1, then the Sylow P group, whatever it exists, then the Sylow P subgroup is normal So if P is the unique Sylow P subgroup, and if we pick any element in G, then you can consider this G inverse PG. In fact, it is a subgroup of G, and the size of G inverse PG is same as the size of P, as the map P from P to G inverse PG, which takes an element P bar to G inverse P bar G. It's a bijection, right? So the number of elements are same. So G inverse PG is also a Sylow P subgroup. So this is we don't need it's a homomorphism, but is a bijection. That's enough. So it's a Sylow P subgroup, but there is only one Sylow subgroup. So G inverse PG is P, and this is true for all G in G. So this Sylow P subgroup is normal in G. So one of the corollary that follows is the following, that if we have a non-abelian simple group, then the size of the normal abelian simple group divides the number of Sylow subgroup factorial divided by 2. That is true for every prime P such that P divides the order of the group. So to prove this, we understand that there is a group action on the set of all the Sylow P subgroups of G. The action is by conjugation. That is to say that G, that is GP, G inverse or G inverse PG, whatever you like. So this is an action. There is a permutation representation for this action. That means there exists a homomorphism from G to the symmetric group of the Sylow P subgroups of G, right? And there are NP number of Sylow P subgroups, so this is isomorphic to the symmetric group SNP. That means the symmetric group on NP letters. So if we look at the kernel of this homomorphism, we know that it is normal in G, but G is simple. That means kernel has to be either identity or whole of G. So for example, if kernel phi is whole of G, that means if kernel phi is whole of G, that means the map is just a trivial map. That means all the element goes to the identity. That means phi G is in SNP, so phi G takes any Sylow P subgroup to itself, but that is GP G inverse is P. That is true for all G in G. So P is normal so as again G is simple, so P has to be either E or P is whole of G. But P being identity is not possible because the Sylow subgroup has order some P power something. It cannot be certainly identity because prime P divides order of G. So this so P cannot be identity, that implies P is just G. So G is a P group. So if G is a P group and we have that it's non-abelian, so size of G is P power some K, where K is at least 3. And we know that the center of P groups are non-trivial, at least for K greater than 2, in this case K greater than 3. In fact, the center cannot be whole because that means that every element then commutes with every other element. That would make G abelian. So the center of group is non-trivial proper. So non-trivial and proper. And in fact, center of the group is normal. That implies that this is not possible. This is not possible. So the kernel of the permutation representation is indeed identity. So we can apply the first isomorphism theorem. We have G modulo the kernel, that's G, but that is isomorphic to the image, but image is a subgroup of S and P. So what we have that G is isomorphic to image phi, and that is a subgroup of S and P. So G in some sense is isomorphic to a subgroup of S and P. So from here we have that by Lagrange's theorem that order of G divides NP factorial, but this is not what we wanted, right? So we wanted that it should divide by 2 again. So our guess here will be that the image phi is contained in the alternating group A and P. To show that, we have to just understand that all the permutation representations are even. So all the permutation representation is even. To show that, let us again understand let us calculate the sign of these images. So G goes to S and P by phi, and S and P goes to this group plus minus 1 by the sine function, right? So and we wanted to show that the sine function is so we wanted to understand that the sign of phi is trivial, right? Is trivial. So this is what we wanted to show. If we show this, then that would imply the image of phi is contained in A and P, because phi takes an element to permutation, and the permutation is even. So phi takes all the elements of G to permutations, and those permutations are even. So the image in that case is a subgroup of A and B, the alternating group. Suppose it is not trivial, then sign of phi is a surjection. So the kernel of sign of phi is normal in G, and in fact we have the size of G and the modulo kernel of sign of phi is the size of image of sign of phi, that's 2. So because the size of plus minus 1 group is 2, so that means that the index of kernel of sign of phi in G is 2, and it's normal again. In fact, one can show that from here that it is normal, but yes, it is normal. Moreover, we are not talking about G equal to C2, because if G is C2, then in that case the kernel could very well be identity, and still the index 2 remains. So what do we have? We are not talking in C2, because C2 is abelian. So that's so that means that kernel is normal in G, and it is not equal to identity, and in fact it is not equal to G anyway. So again we have that G is not simple, and that is not possible. So this establishes the result. Now why this establishes the result? Because now we have image phi is a subgroup of A and P, but image P is isomorphic to G, so order of G divides NP factorial by 2. So this is one instance where we use the Sylow theory. So now let us prove the Sylow's theorem. So in the first Sylow's theorem, we need to show that the set of all Sylow subgroup is non-empty. That is, we have to show that no, this is non-empty. So an order of G was p power a m. So our task in this case is to find a subgroup of G of order p power a. So to prove that, the proof is not quite straightforward. In fact, it starts by looking at the following set, that is the collection of all subsets of G. Note that X need not be a subgroup of G in this case, but they are collection of subsets such that the size of this subset is p power a. So this is a set, and there is an action of G on this set via the following, that is, you take an element of G and you take a set and we can do the left multiplication. So by left cancellation, it is easy to see that in fact this member is in omega, and one can use the associativity of the binary operation of G to show that this is indeed a group action. Now let sigma be a subset of omega, and let that sigma be some orbit, be an orbit. So it may be orbit of some element, right, of sigma, and they are members of sigma, right? So it's a subset of sigma. So the question is, if say G1 GPA, if this is in the orbit, then G1 inverse is also in the orbit. That means this is G1 inverse G2 and G1 inverse GPA is also in the orbit. So what does that mean? That means that the set that means that this set, it contains G, right? So that means that for any G in G, you can find a set X in omega, X in sigma, that contains the G. Okay, so what does that mean? That means that how many elements are there in sigma? That is something that we wanted to say now. So the number of elements in sigma, so it may be very well that every element, since every element are distinct, so the number of element of sigma is at least the number of element of G, and each of these has p power a element, that's p power a, so that is m. So number of element in the orbit is at least m. So now we can divide it into two cases. What if number of element of sigma is m, and if it is greater than m, right? Now by orbit stabilizer theorem, so what is the so we wanted to find the stabilizer of any element, say G1 to GPA is in sigma. So the stabilizer H of say G1 to GPA, the size of the stabilizer times the size of the orbit is the size of the group, that is p power a m. The size of sigma is m, so size of H is p power a. So order of H is p power a. So in that case we have now found a subgroup with size p power a. Okay, that's nice in this case when sigma is m. So the question is, what if the size of sigma is greater than m? Okay, now if the size of sigma is strictly greater than m, then one can show that the prime p divides the size sigma. Okay, so again this is by orbit stabilizer theorem, because size of sigma times size of stabilizer is p power a m. So size of sigma is greater than m, and that means also size of sigma divides p power a m. So in fact it is greater than m, that means it has to contain some factors of p, right? So in that case that implies p divides the size of sigma. So this is why we have that. Now now what happens is that if we are able to show that the size, that p does not divide the size of omega, then what happens is that not all orbit sigma can have size greater than m. So if all the orbits of sigma has size greater than m, then p divides that the size of each orbit, and each of these orbit partitions omega, so size of omega is a multiple of p in that case. So so that means that there is at least one orbit of size equal to m, and the stabilizer of any element of the orbit is of size p power a. Then we are done. So we have to show that p does not divide the size of omega. So to do that, we try to count how many elements are there in omega. So that's these are collection of sets. So among the order of G, the number of phase of picking p power a element. So but size of G is p power a m, and that's p power a. So this is equal to p power a m factorial, p power a factorial, and p power a m minus p power a factorial. Okay, and Now what we can do is we can do some manipulations. So then let's see what can be done. So this is p power a m, and so p power a m minus 0, p power a m minus 1, p power a m, so minus say p power a minus 1, and then p power a m minus p power a factorial divided by p power a factorial, and p power a m minus p power a factorial. So that means this is p power a m minus 0, p power a m minus 1, all the way up to p power a m minus p power a minus 1 divided by p power a minus 0, p power a minus 1, p power a minus p power a minus 1. That is j equal to 0 to p power a minus 1, p power a m minus j, p power a minus j. So we have to show that p does not divide the size of omega. So largest power of p that divides p power a m minus j, again j is less than p power a m, so is the largest power of p that divides j. Similarly in the case of denominator, so the largest power of p in the numerator cancels with the largest power of p in the denominator. So this part is not, so this fraction is not divisible by p. In fact, this extends to the product of fractions. So that's the reason why so p does not divides the size of omega, and that completes the proof of 1. So now we will show Sylow's second theorem also holds. So we have to show that any two Sylow subgroups are conjugate. So instead of that, what we will do is we will try to prove something that is much more stronger. So if we take Q to be a subgroup of G, and let Q be a P group, P subgroup, that is size of Q is P power B for some B, and this B need not necessarily be A. Okay, and if P is a subgroup of Sylow subgroup of G, then we will show that there exists a G in G such that G inverse P, G inverse QG is a subgroup of P. So if Q was a Sylow P subgroup, then we would have the size to be equal. So P is G inverse QP in that case. That means P and Q are conjugates in that case. So it amounts to find such a Q. Sorry, such a G. So to show that, we look at the set of all cosets of G mod P. That means look at, so this need not be a group, so it is the collection of cosets of P in G. Okay, so now Q is a subgroup of G. So what happens is that there is an action of Q on the collection of cosets. So Q acts on G mod P via multiplication. That is, so let us keep elements of Q by small q. Again, the size of orbit divides the size of Q, which is P power B. So that means the size of orbit is 1, or P divides the size of orbit. So if all the orbits are of size P, if all the orbits are divisible by P, then so we know that sum of distinct orbits is the size of G mod P, which is M in that case, and this M and P are relatively prime. So if each of the orbits are divisible by P, then P should divide M, and that is not possible. So there is at least one orbit of size 1. So there exists an orbit of size equal to 1. So we will call that GP. So this is how we catch hold of such a G. So there exists a G such that GP is the orbit, and the size of the orbit is 1. So what does that mean? That means that Q times GP is going to be GP for every Q in Q. That means G inverse QG P is in P for every Q in Q. So that means G inverse QG is contained in P, and that completes the proof. So now we want to show the Sylow's third theorem. So we need to show that NP is congruent to 1 modulo P, and NP divides the order of the group, where this NP is the size of the set of all Sylow groups. So first we will show that NP divides order of group. So there is to understand that why NP divides order of group, this is because that there is a, so this is because there is an action of G on the set of all Sylow P subgroups, and the action is via conjugation. So G P is GPG inverse. In fact, conjugates belong to Sylow subgroup because their size remains same as the size of the group P. So the orbit, the size of this, so we want to find what is the size of this orbit, right? So by Sylow's second theorem, we have that size of the orbit, we have that there is one orbit, there exists only one orbit, and the size of the orbit is the number of Sylow P subgroup, because they partition the set of all Sylow P subgroup, and size of the orbit divide the order of the group, so NP divides order of the group, and that's the reason why. So next is we have to show that this NP is congruent to 1 modulo P. So what we will do is we will take any Sylow P subgroup, and what is interesting to note that this Sylow P subgroup P acts on the set of all other Sylow P subgroup via conjugation again. That is GP is GPG inverse. So again, by orbit stabilizer theorem, the size of orbit divides P power A. That means the size of orbit is either 1 or P divides the size of orbit. So the question is, does there exist all orbits of size P? Then that is not the case, because there is one orbit of size 1, that is, take the orbit of P, right? So you take any element, so this is a Sylow P subgroup, so you take any element P from P, so P inverse is again contained in P, and their size is same, so P inverse is P, so the size of that orbit is actually 1. So to show that the number of Sylow P subgroups is congruent to 1 modulo P, so what we have to understand that this Sylow P subgroup is some k times the size of orbit, where size of orbit is some P power n. There is one orbit of size 1, and there might be many more one orbits, okay, many more 1 orbits. One-sized orbit, and if we are able to show that there are not many more one-sized orbit except P, that means there is exactly one orbit of size 1, then we are done, because in that case the size of Sylow P group is Kp power n plus 1, and that is congruent to 1 modulo P. So for the sake of contradiction, if we have another orbit of size 1, Q be any orbit or let us take any orbit and show that that orbit is indeed equal to the orbit P. So Q be any orbit of size 1. Okay, that means you take any element of P, you have PQ, P inverse is Q. So what does that mean? That means this P belongs to the normalizer of Q in G. Okay, so I think this is a wrong notation. Normalizer of Q in G. So normalizer itself is a group, and we can look at its Sylow P subgroups. What we can understand that is the following, that P is a subset of NGQ and NGQ is a subset of G. In fact, the same holds for Q, because that is true for all Q in Q. So size of P is less than size of NGQ, which is less than equal to size of G. Size of G is P power A M and size of P is P power A. So P power A divides the order NGQ, and in fact it is the largest. So this implies it is the largest power of P that divides order of NGQ. And Q is also a Sylow P subgroup, so size of Q is also P power A. So Q is also, and we know that Q is contained in NGQ, so Q is a Sylow P subgroup of NGQ, the normalizer, and also P. So by Sylow's second theorem, P and Q are conjugates. So P is in NGQ, so P is X Q X inverse, but as it is in NGQ, so this is actually Q. So P and Q are same. So orbit, so there is only one orbit, of size 1, and that completes the proof. So here there is a note that Q is contained in NGQ because it's a normalizer, and XQ X inverse is actually Q. So we have done that, I guess. So we know that actually. So let us understand this with some examples. So I think we can appreciate this theory if we understand some examples. So say the group is GLNZ ZP, that is the set of all invertible n by n matrices. Over ZP, that means entries are coming from ZP, and P is a prime. So firstly we want to know what is the size of this G. So to find the size, it's quite easy, because you take an element of GLNZP. So what does this entries of A are? So if you look at rows or columns, so the rows of A are linearly independent over ZP. Okay, so you can view this as the entries, the rows or columns are coming from the vector space ZP power n, right? So first there are first row or first column has p power n minus 1 entries. Of course we want it non-zero, that's why we have to remove that. And second one has p power n elements, but you have to also remove the linear span of others. So there are p many linear span of others. So first one has p choices, second one has again from first one you can remove yeah, so there are p many linearly because there are p many elements, right? Now for the third one you have to avoid the linear span of first two. So there are p times p choices because there are p and p slots. So p square, and keep doing it, you will get p power n minus p power. So that is the size of GLNZ. So the question that we want to ask is, what is the Sylow? Can we find a Sylow P subgroup of question? Can we find a Sylow P subgroup of GLNZ? So it turns out that we can actually. So it depends on the size GLNZP. So first is p power n minus 1. From second you can take out p. You have this. From third you can take out p square. And from the last one you can take p power n minus 1. So that's p minus 1. So you have p times p square times p power n minus 1 times a multiple that is not divisible by p. So that's p power n choose 2 actually, because you have to sum them up. Times a multiple. So now that means the size of Sylow P subgroup. So size of Sylow P subgroup of GLNZP is p power n choose 2. So the question is, can we find one such subgroup? And yes, it is indeed easy. So so here is an example of one such Sylow subgroup. So unitary upper triangular matrices, right? So this is in GLNZP. That's easy to check because determinant is 1. So the question is, what is the size of this, right? So first there are p choices, then there is p square choices, the last one is p power n minus 1 choices. So the size of this p power n choose 2 actually. So the question is this Sylow subgroup unique? So the answer is no, because you can just think about unitary lower triangular matrix, and that's also a Sylow P subgroup. So let's do one last example. So now let us focus in say GL2ZP, and what is the size of this GL2ZP? Okay, so the size of this GL2ZP is p square minus 1 p square minus p. You can do some calculations and see that this is p square minus 1 p minus 1, that is p minus 1 the whole square p plus 1. Okay, and suppose it's just example, so suppose L is a prime such that L divides p minus 1. Okay, and suppose that the largest power of L that divides the order of the group is L square. Okay, so suppose the largest power of L that divides order of G is L square. Okay, so the question is can we find Sylow L subgroups? So the question here is, can we find so by finding we mean that we want to find explicitly so and the question is, it turns out that we can actually. So the first idea is to find an element of order L, right? And we note that if we look at the units of ZP, okay, the units of ZP is isomorphic to the cyclic group CP minus 1, so P minus 1 elements. Okay, so what we know is that as L divides the size CP minus 1, so as you know that for every divisor of the order that divides the order of CP minus of cyclic group, you can find a cyclic subgroup of that order in the cyclic group. So this implies there exists CL, which is a subgroup of CP minus 1, and CP minus 1 is isomorphic to ZP star. So we need L square somehow. So you know that CL cross CL is a subgroup of now ZP star cross ZP star. Okay, and what happens is that this ZP star cross ZP star is a subgroup of GL2 ZP. Why that is the case? Because the map A comma B say via some phi goes to A00B is an injective homomorphism which is easy to check. Okay, and that means now there is an identification of now there is an identification of an element AB of ZP star plus ZP star to AB. Okay, so you can take an element of Cl and another element of Cl and identify so the image, okay, so the image of this homomorphism, so phi of Cl cross Cl, which is a subgroup of Gl2Zp, is the Sylow L subgroup. So yeah, that's it.